Hello, I welcome you to the update for our respirator. This update is very important that the respirator works correctly, so please watch it to the end. But before we start with the update, I have to give you a small correction of the wiring plan. In the wiring plan of the main video I forgot to paint the bridge of the motor driver. Later I show it to you on a picture. So you have to bridge the pull function and the direction, and then you have to go to the plus of the whole wiring plane. It's important that the driver can work. This is a picture of the wired motor driver. You can see all the wires. There are declared in the datasheet of the motor driver, and this here are the wires to connected with the Arduino, and this is a bridge I have forgotten in the wiring plan. This bridge here you can install it, but we don't need it because we don't use this function. Here you can see the new valve. I've chosen the new valves with stepper motors because stepper motors are more reliable than servos, and this valve is easier for you to build. You don't have to bend wires and you don't have to manipulate the parts in the way we need it for the other valve. Here you just have to assemble the printed parts and the thread rods. We have one flexible shaft coupling, but you only have to cut the thread rods. To move the piston of the valve, you should use a stainless steel thread rod because this is you have here oxygen inside the valve. I've chosen NEMA 17 motors. They have enough power for the valve, and I've chosen motors with integrated stepper drivers. Of course, you can use motors with separated stepper drivers, like we have done it for the pistons for the respirator. Of course, you should use closed loop stepper motors because they are quicker and the piston works quicker with them because they have to go up and down, and we need a high rotation rate. Here you see for the correct function of the valve, it's very important that the piston has in the end position is always the same position. So we need an end stop to correct it always. The most easy way is a light barrier control because we don't have mechanical parts, so we don't have problems with oxygen. This is a LED and this is a photoresistor, and if the piston goes up, he triggers our end stop, and so it stays stable on the same range of the movement. Here you can see details of the piston from the new valve. This is the body of the piston, and inside this body we need a female screw for our threaded rod that the piston goes up and down. I show you later how you can program and stop with a slicer. So the printer stops here. You put in this female screw and then you continue the print. The cover of the piston is made out of a hard material to reduce the friction between the piston and the body of the valve. And Here you can see the threaded rod that we can fix it in our flexible shaft coupling. We have to wind a 0.5 millimeter wire around the head of the threaded rod and put it inside the flexible shaft coupling. And so you can be sure that you have a stable connection between this part and this part. This is very important. This is the STL file for the valve. Here you can see a tube. This is for the LED for the light barrier control. And on the back side you can see the true for the photoresistor. In my prototypes I have printed this tube separately and fixed it by hand and drilled the trues. But here it's easier for you, and they are on all three valves. You have them at exact the same position, so you don't have to adapt the program. In my case, this is a volume. As a volume I have defined the way for the piston, and I have to adapt it for each valve separately. And now you have to try which valve you have to use for the valve with a printed tube, but you have then you have for all three valves the same valve. We need two adapter rings to connect the valve with the respirator. That's the first. This is the second. This is the cover for the piston, and this is a piston with I have illustrated here a little bit transparent so that you can see the hole for the screw and for the female screw inside. This is an imported STL file for the piston of the valve. That you have the space inside for the female screw, you have to print it without support. Here in Germany we call it Stützen, keine Stützen. In English is no support. If you choose with support, the slicer will infill the space for the female screw. The infill of the body is here I've chosen 40%, that the piston will be flexible. Now you go on slicing, and after a short time you get this sliced model. Then you can go here and go down to find the space for the screw. So, okay, here you see the free space for the screw, and you can choose layer of layer, and you go up to the highest layer. Now the blue one, you can see this is the first layer over the screw, so you have to go down one layer. Okay, and then you go on the plus, choose with the right mouse click and insert the pores. Here you can give a comment, but you don't need this comment, and click OK. And now you go on slice again, because you have another G-chord slicing. And this is jetzt now the time. Here you get the pause. You have seen it in the picture before. You put in the female screw, your printer makes your pause and gives you a sign that you can continue the print. And then the rest will be printed. And this G-code you have to export on an USB stick and put in your printer. And then you have the part inside with a metal female screw. For demonstration, I have positioned all the parts or the printable parts for the valve on this platform. You have to turn this part in this direction and the valve in upward direction, and then you have to print it with support. Because otherwise this tube and this plane will be not printed correctly. Of course, we cannot print all those parts together because we here need for this the body of the piston we need flexible material, and both parts are printed with normal filament, but just to demonstrate. If you have the parts printed, you put this flexible part inside the cover for the piston, and then you have to turn it, and the piston here goes up and down in the valve. And because the layers are in a 90-degree angle together, these both parts cannot cut together. This is important for a low friction. Here you can see Arduino Nanos. We need them for the steering of the valve and for the steering of the light barrier control. The codes for the steering of the light barrier control and the valves are very easy, so Arduino Nanos are enough, and they are cheaper than the Arduino Megas. An Arduino Nano has soldering pins, so you can solder the Arduinos direct on platines. I prefer platines with conducting paths and not them with single soldering points. I've cutted the conducting paths between the both sides of the Arduino, except 3 lines here and 1 here. So in this configuration it's more comfortable to solder the rest of the electronic parts we need. I show you what you have to do in the next picture. Here you can see a switch. This is a chamber in which the air is cleaned. We do it with a UVC bulb, and if you open the chamber, the switch turned off the bulb because the UVC light is dangerous for your eyes, and so nothing can happen. And this is the inside of the valve. Here you can see the light of the LED, and this here is a photoresistor, and here's the LED, and if the piston comes up, the light barrier control gives the signal of the end stop. The biggest difference between the actual version of the Respirator and the former version you have seen before is that I have changed the unit with the pistons and the cylinders into a unit with bellows. Here you can see 2 bellows. You just have to print these rings and the slits. I have fixed the bellows with cable fixers on these parts. You also can use pipe clips. Then you have to fix the open ring into the basis, and you can mount the whole thing into the respirator. It is very easy to change the unit, the old unit into the new unit, because all the rest you can let stay. You have the blank, which is moved by our stepper motors, and you just have to fix this part onto the blank and change the unit. Here you can see the end stop. It is mounted on the basis of the bellow unit, and here I have fixed flat washers to the ball screws, because if this part rolls down and falls down, it is destroyed. You can't put it, you lose the balls inside and you cannot remove it. So you have to buy a new one. If you need a new ball linear drive and order it, it comes into a plastic bag that no dust can come inside uh, this part. Here you see a plastic tube. If you want to replace the ball type linear drive, you have to stick this plastic tube on the ball screw, and then you can wind up it without losing the balls inside. This here is a unit with the cylinders. These are the old pistons. These are two pipe clips. If you don't want to use cable fixers to fix bellows on the printed parts. This is a tool to tighten the cable fixers if you use them, and this picture shows the wooden blank like it looks in my respirator. Here you can see the recesses for the valves, for the ball screws. These big screws are for the copper tubes, and the small screws are to fix all these parts with cable fixers. Here you can see two examples of bellows. The manufacturer is Dynatec and the distributor is Steinbock Industries, but it doesn't matter. Important are the technical datas. The minimum diameter should be around 80 millimeters, the maximum between 110 and 120, and the difference between the minimum length and the maximum length should be at least 220 millimeters, that you have enough volume for your respirator. This picture shows you the wiring plane for the valves. Here you can see the stepper motors and the stepper drivers, and the Arduino for the steering of the stepper driver. Of course, you have to split this two wires in each three parts, because we have three valves, and so we need this 3 times. This is the Arduino for the light barrier control. You can use 3 of these Arduinos, but also you can subsumit 3 of the light barrier controls on one Arduino. In the code you will see that I have used 3 pins for 3 photoresistors. It's cheaper to make it. Here you have the voltage, 6 volts plus, this is ground. If you want to use this Arduino for 3 valves, you have to split this wire in each 3s that you can support the LED. Take care that you use for each LED a separated resistor. Uh, it's the same for the photoresistor and here for the pull down resistor. This LED is just a control that you can see if the light barrier control gives a signal to the stepper driver or the Arduino, which is steering the stepper driver. Uh, it's useful to develop or to change uh, the code, but in the normal use you don't need this LED, this resistant, uh, and this wire here. This part you can, you don't need it. Now we have to talk about the codes. I have a little bit improved the code for the Arduino Mega, which is reading out the sensors so that the respirator can react a little bit quicker on the breath of the patient. If you want to use the new type of valves, you have to download a new code for the other Arduino Mega with a touchscreen display, because the new code can correspond with the Arduino Nanos for the new valves. Here you can see the code for the Arduino Nanos for the steering of the valves. This is a code for 2 of the 3 valves, for the incoming air in the respirator and for the outgoing air from the respirator and the cleaning chamber. The second code is for the valve which is managing the air for the patient. They are nearly the same, only the directions are in the opposite. For this code we only need one interrupt call because we have only one end stop. This is a code for the light barrier control. It's short and simple, and here you can see that I used one Arduino for 3 photoresistors, so we can control with one Arduino all 3 valves. For the reading out the photoresistors we have to use analog pins. It's analog 0, analog 1 and analog 2. The signals to the valves we give them with the digital pins. We have used here pin 3, pin 4 and pin 5. Between the directions of the piston we have to program a little bit of delay. It depends how quick your motor driver and your stepper motor can change the direction. For the tip type I used 8 milliseconds are okay. In the data sheet they said 6 milliseconds, but I'm using 2 more. The Arduino and the microcontrollers are very quick, so it doesn't matter. We read out the photoresistance almost simultaneously. This is a reaction, the valve where the light barrier control reacts. You have to change it a little bit. It depends of the brightness of your LED, which gives the light for the photoresistor. Here you have to try it. Maybe you can use 200 or 300. It depends, as I told, on the brightness of the LED and of course of the color, of the valve. If you use a white one and comes light from the outside inside the chamber, you have to choose here another valve. If you use black filament, it's better because you don't have light from the outside and you have nothing to irritate the photoresistors. Here you can see both wiring plans together. Uh, that you can see it's nothing to change here. You only disconnect the servos and connect the blue one to this blue one and the yellow wire to this yellow wire. Uh, of course, you have to split these wires in each 3 wires, and you have to connect the plus of this with the plus of this here and the minus or ground to the ground. That's all. Sometimes on my respirator, if it's running for a longer time, I've got problems with reading this sensor and the whole thing don't works. At the first time I thought the sensor was defect, but it wasn't. So I've just put here a switch and I can disconnect the sensor and reconnect it, and it's like a reset. I don't know why, but if you should have problems, if this is the reason, you cannot change or stop it with this button. The respirator is just automatically running. It could be the reason that you have to reset the sensor here. On this schematic drawing you can see the positions of the 3 valves. You need 3 valves. It doesn't matter whether you use the new type of valve or if you use the old valves. The first valve is regulating the oxygen which flows inside the pistons or inside the bellows. The second valve is to regulate the air or the oxygen which comes out of the pistons and goes to the patient. And the third valve is for the regulation of the exhausted air from the patient. If the bellows or the pistons are going down, the air flies from the pistons to the patient. So this valve is opened and this one is closed and this one is closed, so that the air or the oxygen only can flow into the lung of the patient. If the pistons are going up, we have to close this valve and to open this and to open this valve. Here the new oxygen flies inside the pistons or inside the cylinders or the bellows, and here the exhausted air of the patient flows out of the patient in the cleaning chamber. The new valves need 2 Arduinos to be steered, one for the stepper motor and another one for the light barrier control, but you can use, instead of 3 Arduinos for each light barrier control for the valve, you can use only one which operates all 3 light barrier controls. If you use the old type of valves, you don't need this Arduinos. Of course, furthermore, we need the emergency valve so that the patient can inhale even if the respirator has a failure, and we need the PEEP valve so that the patient has always a minimum pressure in his lung. On this picture we can discuss the function of the respirator according to the breath of our patient. Here you can see the three new valves. These are the bellows. This is a PEEP valve that we have always a minimum pressure in the lung of the patient, and this is the emergency valve which opens if the patient wants to inhale and the function of the respirator breaks down. So if the patient wants to inhale, the pistons are pressed down. In this time, this valve is closed and this valve is opened, so that the oxygen flows through this tube, and this tube inside this box. The box is shared, and inside we have UVC light. The fresh oxygen flows through water and goes on this tube to the patient. Then the patient wants to exhale, so that this valve opens, this valve closes, and this valve opens. In this time the bellows are pulled up, so that fresh oxygen flows inside the bellows. And this is repeated with each breath of our patient. Here you can see the two options for the respirator. This is a medical mask and this is a snorkeling mask. If you use the snorkeling mask, you don't need the third valve for the respirator, because the snorkeling mask has integrated this valve here inside the mask. This is a Google Drive folder where you can find all files you need. I've tried before to upload a small update, but YouTube don't accept too short videos. So I have to wait to now until I have finished the valves. In future I will only upload the updates on this folder, so you should watch from time to time here. Maybe you can find some improvements for the respirator.